Good morning. Next slide. A second. It's not from the start. Here we go. So my name is Ivan, and I am working for the company called Archetype AI. It's a very new company. We just started 3 months ago. I'll tell you about it in a second. So I would like to talk about physical AI and what I mean by physical AI. It's kind of a new form of AI we're building right now. And I go for a little bit to the back. So I've been always interested in fusing physical world and computing. I've been working on this for the last 20 years and built a lot of experiments there. I actually started in virtual reality. This was me in 1996 in the metaverse. And even then, in the 90s, when I started working on virtual reality applications, it really felt dissatisfactory. The fact that you live in a virtual space and replace all your friends with this virtual avatars and kind of hanging out there felt quite awkward. And I like computer games like anybody else, and I like to chat with the ChatGPT and talk about the big questions and have discussions. But I think it's in the physical world where real things happen. Right? That's where we build things, and we create things which is important. That's where we play with our kids or ourselves. That's where we grow our food. And that's where we have all the serious problems right now in the world, which we need to take care of. They don't necessarily happen in the digital world. It's a physical world we have a problem. The complexity of them just grows, and we need help to make it, to improve it and make it better. So, let's see. So, over the time, I started thinking about how can we move from digital reality, which we're kind of building, and computer scientists all over the world have been building for a long time, and it's sort of an alternative reality, which can kind of replace and substitute the real world, to move into another direction, which is called enhanced reality, where artificial reality coexists and enhances the real world. And it's an old idea. I'm not the one who invented it, but it's been since maybe the days of virtual reality, people start thinking about it. And what's important about it is that in digital reality, you can access either physical world or virtual world at the same time. So this is sort of either one or the other. There's a boundary between them exist. While in physical reality, in enhanced reality, you can have both physical and virtual at the same time. So, and that's the power of this enhanced reality approach, extended reality approach, where you can combine the best things of the world. So it's sort of like almost one of these great deals you get on Thanksgiving in America, in Walmart. So you get one, get two for one. Both together, you can use at the same time. And I think what's exciting right now is that with advanced sensors and technology and AI, now building this kind of enhanced reality is becoming more possible than ever. We're really coming to the age when it can be deployed in the real world. And the question is how? What are the possible techniques to build this kind of enhanced reality applications? And I think there's multiple applications. The way I approach this is that, can the world be your interface? So instead of creating the whole new parallel way to interact with the digital world, can the physical world be augmented with technology in a way so you live a normal life and your life is being enhanced by technology? And I'm going to talk about 3 things today. It's a big topic and we can talk a long time, but I'm going to talk about 3 things today and 3 topics which I've been working on, show some of the projects, how we build it over the time, and I'll also end with talking about something we're working on right now. So I'll start talking with how can we go from computer interfaces, from mouses and keyboards, to physical things like interfaces. So when you use the physical things, they actually form both a physical interface to the physical world, but also virtual interface to the virtual world. This is a project I worked at Disney, where we built a new sensor where you can take called sweat frequency capacity sensing, where you connect a wire to the things like a doorknob, and now the doorknob can understand how you're touching it. So you can see that it recognizes the gesture. It's been done in 2012, but it's still quite exciting what it can do. So again, you're taking a wire, a single wire, you connect it to the regular doorknob you buy at the store, and then it can understand how you're touching with a single finger, with a pinch, and with the circle. The important things there is that the interface is universal. It doesn't have to necessarily work with doorknobs. It can work with human body. It's not how you can fold your hands and how you're touching your own body. So you can know you can touch your 5 fingers, you're grasping it, and touching your head. So again, this is a very natural single interface universally can turn physical objects into gesture interfaces. Now, it doesn't have to necessarily to be humans or doorknobs. It can be things like a plant. So as you move your fingers across, the same sensor, as you move fingers across the plant, it can understand the way you touch it. So you can play with it like with theremin. Or you can create a little calendar application. I don't know how we would do this, but nevertheless. So we put it, actually, I was working at Disney at the time. We built for Disneyland. So it was used in the park. And it's amazing how a physical object in Disneyland can be changed and become kind of magical. And the kids really like it. The kids really intuitively understand what happens. Adults gets too. He's like, all right, magical plant, whatever, seen this before. Mickey Mouse came over, the boss. He liked it. So like, this is awesome, haha. Anyway, so this is kind of an example of how it can be built to take physical objects and turn them into interfaces. My second topic I will talk about is how do we go from digital spaces, in creating like windows and virtual spaces, to interactive physical spaces, where physical spaces becomes interactive. And then I'm going to talk about my work I've done when I was at Google. The previous one was at Disney. And in Google, we invented the whole project called Soli in order to make it happen. Soli is a world first and the world's smallest speaker radar. So we build this radar. Usually radars are gigantic things you put around in space and so on and so forth, in the airplanes and stuff. This is a very small radar we built specifically for consumer applications. Actually, it was started like this. This is a box I put myself. And then it was shrink down to a little chip. I worked with a small company, with a large company in Germany to make it actually radar. It was the world's first radar. The way radar works is that it emits an electromagnetic wave and captures a reflection from your fingers. So the reflection from your fingers coming back to radar, and it creates this kind of wave in the computer. And so then what happens is that when you move your fingers, the reflected wave changes. Right? And you can capture those reflections and understand how you move. Now, the picture you get from there is nothing like that. You don't get anything like this, right? You get something like this, which is a superposition of multiple signals combined together with variety processing. There's absolutely no way to understand this and define it by using a heuristical approach. Computer vision people, they like to find out things and figure out how to do stuff. You can't do any of that. You have to run machine learning and AI to understand the signals. It's the only way to do this in an effective way. So we've built that. And the difficulty is a lot of difficulties to work with radars, but they have amazing properties. And two amazing properties there is that work through materials, so you can build them in different things, and they're completely invisible. They go through the textile, they go through plastic, but also they're extremely precise. They're allowed to capture things like heartbeat or breathing just remotely. So we spend a bit of time, how can we build a grammar, a physical grammar in a space where people living in space without actually devices, and based on the radar. So your body is your interface. That's kind of was our method. So you don't need to get into using devices. You don't need to do special things. Just by physically using physical body, you should be able to interact with the devices. So we build a whole grammar based on presence, multi-user presence, natural gestures when you lean, or physical gestures with your hand. Let me show some of the examples. We starting with the hand gesture techniques. If you start here, our approach here is that, like, in order to interact with most of the devices, you don't need an interface at all. Your hand is a perfect interface. Whenever you use a mouse or when you use a keyboard for the phone, your natural gestures in the hand would be like, if I have a phone and use my phone, if I remove my phone from my hand and use my hand like that, the gesture would capture the interaction with the phone. So why your hand can be just an interface? Why we can replace the hand with the gestures where you have a virtual controls like in your fingers. So any gesture represents, for example, a dial like this. Or you can turn your hand around and it's become like vertical dial. Or it can be a slider. If you can capture those motions, remember, radar is very effective to capture these kind of motions, very fine motions. Or it can be a button in space. So that's so the entire your hand turns into a computer device, like it becomes like a mouse or keyboard, and you don't need to have any devices. In this case, this is our kind of the conceptual video when you can control devices just by using your fingers around the device if you have a radar there. So we actually built one. This is the version of the device running in the watch. So you can control this whole thing. But you also can do things like using this for the controlling games. It can be any kind of gestures, right? So in this case, it's puppeteering little character. And the faster you move your fingers, the faster it runs, and it's going to turn into a plane in a second because it pick up enough speed. So you become a plane. And I can do it again. It's a fun game. You can play the whole day. It's actually surprisingly difficult to do that. It's not easy. Your fingers get really tired. So we released solely radar in a mobile phone in Pixel 4, and it was used mostly for large gestures. We didn't get to small gestures. Let me talk about another approach to interaction. It's like, how can we use a body gesture to express your intent? And our body is extremely expressive. The way you lean, the way you sit, the way you act, completely expresses what you feel and how you think. So this picture really illustrates really well. So what if we can track people, understand how people move in space, and depending on what they pay attention to, we can understand what people are interested in. So this is using our radar, and we can see it track how people move around in space. It's very simple monitoring. So we can create a space where people can move around, and we can understand people's interests and people's intent by how close and how much attention they pay to the objects. So when he moves away, you cannot see it. When he goes away, it means he has no interest. And now you can build very, very simple interactive scenarios where a device can be reactive. When you're coming in, it comes up. So if you're just passing by, nothing happens because you don't pay attention. Attention is not important. And if you just turn to devices, it can look back at you. So all the simple expressions can be done by using radar or any other techniques. And what's interesting thing about radar is privacy preserving. Whatever you capture with radar, you don't see a human, you just see the motion. So we capture motion and not capturing the images of the people. So we actually launched some of these use cases in Google products. It was a Nest device. It's actually, you can buy it in a store, but we use it for tracking sleep. So when you lie in front of in the bed, it understands how you're breathing, it understands how you move during your sleep, and it measures your devices, your sleep pattern. But what's exciting here is now you can put these things together. You can put a interaction with the physical object and the physical object of the interface and spatial interaction space to build full interaction scenario. This is a system we built together with one of the clothing company which want to show how we can interact with objects in the store. So as you coming close to the display, the more details coming out about the product. And for example, as you becoming even closer to materials, now it increases and shows you the details of the object. So it's very naturally maps interaction. As you're interested in something, the closer you come in, the more details you see. Let's see again. So when you're outside of the in the overview zone, further from the display, it just shows you what the product is. And when you come close, you can see the features of the product. And you can even close, you see more features. Obviously, it can be scaled to any products or any things you're trying to use. But it creates very natural progression of how space and interaction with objects can be mapped together. So I would like to talk about a third topic right now. So with all these use cases examples, we build many different use cases. We can turn physical objects into interaction. We can turn spaces into interactions. The problem there is that there are millions and millions of things and spaces in the world. And how can we make them all intelligent? It just doesn't scale. Are we going to write machine learning model for every single object? Are we going to put electronic in every single object? How we can connect them together so it works as a system, it's not separate objects? So one insight we have is that like one technology which came up recently, obviously, is large language models, artificial intelligence. And we're building all those use cases you saw are based on machine learning, basic machine learning techniques. But what's incredible with the LLMs, and like GPT-4 and GPT and all these models, is that they have a variety of world knowledge built into the models. So can we use the world knowledge captured by large language models and use them as a tool to interpret of all the interaction in the physical space instead of us trying to write those algorithms themselves? Can we automate and make it completely autonomous? This is an example of a simple question. We're asking, look, can you describe physical movement of the person approaching me? And it gives you exact description of what's going to happen. So if you can capture those descriptions, you can understand, use LLM to interpret what happens in the physical world, versus all the previous use cases, we have to write it by hand. So what we're proposing, what we decided to do is that we would like to build a multimodal LLM that can autonomously interpret real-time sensor data and reason about the meaning of that and answer any questions to humans about it. So you don't have to have software developer who can do that by himself. So you have basically a physical world. You put any kind of sensor, radar, cameras, recorded data, not recorded data, any kind of data can be captured by the physical world, and it goes to a single model, and then the model just tells you what's happening in the real world. So you don't have to even write a software about it. Right? So you just write one model. That's kind of an idea we had. And basically, we're talking about building a foundation model for physical reality. Physical reality is captured by sensors. So as long as you can interpret sensors, you can build a foundation model which can understand the physical world. And that's the company we launched called Archetype AI. We launched it 3 months ago. My team was at Google, 5 people. We left and started this company called Archetype AI to build this idea. We want to build a foundation model for physical world. Similar how you have GPT-3 or GPT-4 for language, we're going to build one for physical reality. And I would like to show you for the first time, we just announced it about yesterday or the day before yesterday, we announced the company publicly. I would like to show some few examples. I've never shown them before. What kind of things we can do? Because the first thing we start doing is that I put together the sensor information and large language models and see what kind of interactions you can build. Very simple examples just to show what's possible. So this is an example of we capturing the camera data and feeding everything to LLM. We modified LLM. So now you can ask those questions. What happened today? So it takes all the videos, summarizes it, and this is a real-time video, and it says, a group of people were having fun playing toy giraffe in the pool, and the package was delivered at the front door. So instead of you going back on the video and scrolling and finding out what's happened, you can just ask a question, and it'll summarize your video and give you the answer. So now you can ask the model, can you please show me what's happened? Can you show me deliver the package? So what LLM does, then our model does, it generates the code which goes to the video and pull out that video straight from the code and just show you the video, pull out the video where the package is being delivered. So again, you can start using natural language to ask what's happened in the physical world, and the model pretty much gives you interpretations. We didn't write any code for delivery object, or reinterpreting this video. It's all done by LLM. But what's the interesting thing about LLM, you can ask very general questions. You can ask questions you could not ask before. This is a regular query. Show me the package, show me the person. But you can show something, ask something. Show me a fun moment. And let LLM to figure out, language AI will figure out what does mean fun moment. And it goes to the left video and try to generate the context. And it finds the moment where the kids were playing with giraffe in the pool. All right, so it's understand what's happening in the video, collect the labels, interpret them, and figure out what happens. So this is very exciting. Exciting thing here is that you can now ask very generic questions about questions you could not ask before, high-level questions. This is another interesting example. Not everything can be done by audio. So our model could not understand certain things, but we combine audio and video in the same place. This is a TV show, and she's cooking. At some point, she poured the glass of the water, of the juice. So can you show me when she pours liquid? And this query is done by audio, not by video. It looks for audio of pouring sound and pulls out the video of your pouring from the things. So you can start combining multiple modalities and using both modalities to find information you like. What you also can do, you can do localization. So as you go through space, you can capture what objects around, and you can interpret where you are. So you know you're outdoors, you're in a residential area, you're in the street, you're in door room, you're in garage, mistake, not the garage, obviously. Home office, and it's all done completely semantically. It's semantic localization, it's semantic search. So you don't need to track people. It understands just like we understand where we are by looking at things around it. our AI can understand where you are just by understanding what objects are there and putting them together. Something which was not done before. Again, we didn't program everything. The same model does all these use cases. And then what you can do now, and this is kind of like really, you have to see on the video on the bottom. Now you can ask much more complex questions. You can ask generic questions related to particular context. You can combine high-level questions and the context. So you're asking, alert me only when there's sharp objects in the living room. So what it does then is compute what does it mean, sharp objects, and figure out there's a knife, scissors, fork, spoons, bottle. I don't know why bottle there, bottle. And it understands these are sharp objects. And now it's only alerts you when you're going through physical space and through the room. So when you look at the scissors in the kitchen, it did not alert you. But when I see the scissors in the room, in the living room, it combines information about living room and the fact that I see scissors, one of the sharp objects, and it alerts you then. So this is when we're showing to some of the potential customers, people were excited about this because you're reducing false alert or reducing false messages dramatically by using this whole thing. So you detect the scissors and within the living room. Now what you can do next then, you can start adding more complex spatial information. And I talked about the radar, so we're adding radars into this space. And now you can have even more information. So there's a radar data, audio data, and visual data all combined in one stream going to the large language model. And what it does is understand there's somebody in the kitchen around the microwave. And you can ask questions, how far away is she? And there is no special code written about the distance. It kind of pulls out and tells it's 0.7 meter away. And you can ask where she's going. And because we know direction of movement and acceleration to certain points, we know how the person moves in space together with information from video. And she seems to approach a microwave. And then you can ask the question, why? And it's try to answer. As a she's preparing a meal and needs to use the microwave. What's interesting here, when we disconnected radar and didn't use the radar, the LLM would answer, I don't know why. It's only when you add spatial information and combine information of person moving in space with specific objects when they'll be able to interpret it and tell you what's happening. So what's exciting here is that when you think about physical AI, the way we define it is that we're going through the designing single use case applications. When you define a ML model or AI model for this physical object, for the mobile phone, for the smart speaker, for the smart lightroom, we write a single model, go away from that, kind of like verticalized way to develop application, to a single model which can understand your interaction, understand your use case with everything. And that, I think, brings vision of extended reality next step forward and really makes it possible. And that's what we call physical AI. A single foundation model that understands any sensor data and combination of them and can explain what it means in plain language. It can just tell you what happened in the physical world versus you having to figure it out yourself. So, and I'll show just a second. And I'll finish my talk by showing a little video we put when we launched the company. Just came out like a couple of days ago, just to explain what we mean by physical AI in a very simple way. Thank you.
Thank you so much. That was fascinating. Thank you. We do have some time for questions.
Really? Yeah, great.
Yeah, we have some time for questions. So there is anybody who asks the first question will be first in line for lunch today. So don't be shy. I'm happy to, oh, here we go. We have one over here. If you don't mind standing up and saying your name, that would be great. We have a microphone coming around. Come on, here he comes. Thank you.
Okay, it's on. Hey, I'm Nicola. Thank you for the presentation. It's an incredibly interesting topic and amazing work so far. I wanted to ask you, how are you accounting for the possibilities in such a large model of hallucinations and capacity of bringing these big models to everyday life and common people? You know, the inference time, the costs of such a huge model are not trivial at all. And at what pace do you believe this will happen?
Which one? So last question. So I'll answer one by one. So the first question about hallucinations. I mean, we are very early, right? I mean, I don't have all the answers right now, obviously. But our early experiments demonstrate that the sensor data actually reduces hallucinations because it grounds the model on real events which happen in the physical world. We have a source of truth. What you sense by sensors is real, right? So whatever we feed into the model is real. Now, if you ask some certain questions like why people doing something, why people not doing something, that's where we probably get hallucinations. But basic stuff, like summarize events, what happens in the world, like give me video of what's fun happens, or something like that. Hallucinations, there are very little hallucinations, we find out. And of course, obviously, would have additional work need to be done to reduce unnecessary hallucination, but that's going to work in the future. But overall, I feel that in the physical space, you have a ground truth. It's physical world, right? That's number one. And second question was?
The second question is, this model that takes in account various kind of inputs and wants to work on various tasks, obviously will not be small and will not be computationally cheap. So at what pace do you see this coming into everyday life for common people?
For the common people, I don't know, but I think our company right now focusing on enterprise customers, right? Who has, we are talking to a lot of people who have a dramatic amount of multimodal data, which they have and they cannot use. There's a lot of factories and enterprises which, for compliance reasons, like we talk to the factory which collects huge amount of data about the factory flow, videos, environmental data, time series data, and they simply cannot use it. Right? So I think initial entrance, initial kind of rollout of these physical AI models is going to be focused on using data in sort of like, not such in real time, but with sort of delay. So you kind of ask questions, maybe 10 minutes later you get an answer. It's fine with them because they just have a huge amount of data which you cannot use at all. And interpret that, too expensive. We are working on a real-time component, and there's two approaches we're taking. One of the approaches is basically creating cascading models, where you break down large model into sub-pieces, and then you progress it, so the simplest questions get answered early, and as questions becomes more complex, and more complex, it takes longer time, right? And more expensive too. And the second approach we're working with quite a few companies is the approach called distillation, where you have a very large model, but for a very specific case, you train a very small model which does about that particular case, and the company delivers that model for their product. And what the benefits from there is that they don't need to write this model themselves. They're using our model as kind of this mother model, which clones these tiny models, which can rapidly deploy it, and update as needed. This is our approach right now. But I think space is developing very quickly. If you look at models today and models yesterday, there is a lot of work happening to optimizing performance of this model, shrinking them. There's examples of running large models on like laptop, on Mac, and so on and so forth. So I think we will see that optimization techniques will kick in and becomes much more effective. And second, hardware optimization is going to kick in. I think there is going to be very specialized, specifically for the real world, there's going to be specialized hardware, and I'm talking about semiconductors component, which can be built, which can optimize the most time-consuming task, which relates mostly to sensor processing. But building, for example, embedded spaces on a chip versus trying to compute it on in software, right? So I think we'll see more and more work going in there. I remember in the 90s, for the first time I saw the MP3 player, right? MP3 player, you would not be able to play without, the whole MP3 thing with Napster and everything else happened because there was a small company built a little chip which implemented MPEG player on the MP3 codec on a chip. And then suddenly all these players came out. Before that, it was impossible, too computationally expensive. I see the same kind of dynamics happening here when certain things are going to become on the hardware. Right, did I answer your question?
Yes, you did.
Thank you. We have some questions over here. We have a microphone coming your way. If you don't mind standing up and saying your name. Thanks.
Thank you very much. My name is Nadine. I'm from Ames, Rwanda. That was a very interesting talk. So I have one question related to the use of gestures to control like computer or the telephone. So we normally use fingerprints to lock the phone or the computer. So then when it comes to use gestures, will it consider the fingerprints or it can be used by several people? Like if I use a computer, I use the the gestures of my finger, and this person also wants to use the same computer that I'm using. Will it consider the person, or it will also consider anyone who can use it? And about the security of that device, will it be locked by using, again, fingerprints, or there will be another way of locking that specific device? Thank you.
I actually am not expert on what you're asking is a question of authentication and how we can authenticate people who are using different devices. That's actually not my area. I did work a lot of closely when I was at Google. I worked very closely with a lot of people doing authentications. The fingerprint is cheap. That's the main reason people are using it. It's very inexpensive to add fingerprint reader. But I think other forms of biometric authentications obviously is going to be appearing as long as people feel comfortable with them. Because there's a balance between technology capabilities and also people's social comfort about them. When Apple came up with a face authentication and using basically a dot projector, laser dot projector to project on your face a grid, and then read this grid to understand who is this person, it took a bit of a time for people to get used to the idea that your face becomes the kind of password for their computer. The humans has a lot of different unique capabilities. They include both things like heartbeat. Everybody's heartbeat is different. Brain waves, retinas, the motions, particularly motion of your hand, highly unique because it's defined by unique neural processing capabilities of your hand and motor abilities. So all those things are will probably going to be explored and released to the market, depending on the use cases, depending on the deployment. I don't think there's a shortage of ideas how to authenticate the user. It's a cost versus applicability where we were trying to figure out.
Thank you. Yes, we have time for one last question. I think there was one up here in the front. Thank you. If you don't mind, the microphone's getting passed. If you can stand and say your name, that'd be great.
Hi, I'm Filippo. The presentation was amazing, thank you. And especially I like the fact that it was focused on multimodal learning and multimodality. I was wondering how with large language models are we embedding into our prompt through prompt engineering or whatever techniques information that are not textual, so tabular or time series data. Have you used LoRa, parameter efficient fine-tuning, or other retrieval augmented generation techniques? How are we handling the multimodality into the transformer?
That's a good question. We're playing with all the techniques, LoRa, and there's a bunch of new techniques recently coming out. But the core idea, the core kind of our bet as a company, which we'll see if it's going to work or not, and that is, its hypothesis, is that you can create a single embedding, space of embedding where you can map any form of sensor data as long as you have mappings between sensor data and known sensor modality, which can be text, which can be video, which can be something else. For example, for the radar, what we're doing, we're capturing radar with images and the radar signals together, and then we cross-reference them and label the radar data with the images data and with the text data coming from images. And we do this together. And for that, then we're training our model with those pairs, just like DALI, but now you have, instead of images, you have the radar data, which is being cross-referenced within the model. And that allows us to pretty much submit text inquiries and get both image data and radar data at the same time. Or you can submit image data and get corresponding radar data, right? So this is all possibility. Basically, right now, that's what I think is the next step. Multimodal models is going to be coming up very rapidly. So we started thinking about these ideas about maybe 3-4 months ago. And we kind of think, oh, we're ahead of everybody. But now, OpenAI and everybody else coming up with multimodal models. So it's going to be anything in, anything out, because all the modalities is going to be mapped to the same space and with single presentations. So the way we explain it is almost like the concept of Rosetta Stone. Like the famous stone which they found in Egypt, where they map different languages together. The same thing is going to happen with the sensor data. We're going to map all this sensor data in a single space, and then you query it using the same techniques. So the prompt comes at the end. Once you remap it, the prompt comes at the end. This sort of hope.
Thank you. Thank you so much.
Thank
Please
you.
give a round of applause to Ivan. Thank you.